Welcome to Positive Physics. Today we're looking at radio and microwaves. So, the frequency and wavelength of radio waves is a range from between 3 times 10 to the 5 Hertz to 3 times 10 to the 9 Hertz. Now hopefully you've been learning your prefixes, okay, so we would probably convert that to 3 gigahertz, and 3 times 10 to the 5 would be 30 kilohertz. The wavelength is between 1 meter and 10 kilometers, and because they are electromagnetic waves, they can all be reflected, refracted, diffracted. They travel at the speed of light, 3 times 10 to the 8 meters per second in a vacuum. And every single electromagnetic wave will have these properties. Now, radio waves, how are they produced? Well, it's actually quite straightforward. What happens is, if you have an alternating voltage, so a voltage which is changing direction with a specific frequency inside a piece of metal. So our current, and therefore our voltage, is always changing direction, and it's going up and down. Well, that change in voltage is creating a radio wave every time there's a change with the same frequency that the voltage is changing. When that radio wave reaches an aerial or another piece of metal, instead of just staying as a radio wave, what it does is it puts a force on the electrons in the wire, and it induces a voltage which changes, an alternating voltage in our aerial. So our transmitter has a changing voltage, an alternating voltage, which creates a radio wave which, when transmitted through the air at 3 times 10 to the 8 meters per second, because it's an electromagnetic wave, is received at a receiver and then will induce an alternating voltage in that, which can then be either measured or it can be converted into sound. Now, there are two ways that radio waves are transmitted. AM, which means amplitude moderation, and FM, which is frequency. I've just recently realised I've written moderation, modulation. So that should be modulation. My apologies. So amplitude modulation means that we have a carrier wave with a certain amplitude. And then we add the radio wave with the sounds we want to transmit, which will have a different frequency and shape in terms of its amplitude. And we add the two together and we end up with a wibbly wobbly wave. But that wibbly wobbly wave, when it's received at the receiver and the carrier wave is subtracted, because we know the frequency and amplitude of the carrier wave, gives us the sound that we want to be converted in our radio receiver. Frequency modulation works very similarly, except the carrier wave has its frequency adjusted. So rather than being nice and smooth, when we have something with different frequencies, we end up with some areas of low and then some of high frequency and some of low. Okay, that's not specifically on AQA GCSE, it's a little bit of extra information. Now, radio waves are brilliant in that they can be transmitted a long distance. But if we want to transmit television or a long wave radio, they have a different wavelength, as the name would suggest. So for a television signal, they have a very short wavelength, which means that as they're transmitted, they pretty much can only travel in a straight line. And if you're not in the line of sight of your transmitter, then you won't be able to receive the television signal at your house. If we're using radio waves. If you're on cable, different story altogether. Now, long wave transmissions, so a long wave radio, is transmitted at a much larger wavelength. As we've said, it can be up to 10 kilometres. Now, the chances are that you'll find in a situation like this, you could have two houses that are approximately the same distance as the crow flies to the transmitter. This house here, let's call it A, will receive the short wavelength TV. But this house here won't receive it. But this is where the cool bit comes in, because longer wavelengths will be diffracted through this gap. And if this gap here is the same distance as the wavelength of the longer wave radio waves, then we get maximum diffraction, and we'll see this house will be able to receive it. So if our wavelength is about that distance, so what I'll do to show the wavelength is I'll have the difference between my between my wave fronts as about the same. Then I get maximum diffraction as it goes through the hill, the gap between the hill, and the waves continue to spread out, and they are reached. They reach both houses, A and B. So, although this house won't receive the TV signal from this transmitter, so there would need to be another transmitter, or they might have to use satellite or cable or some other form, they would receive the long wave radio, because the gap between the two hills equals the wavelength of the radio waves, and so it is diffracted between the hills. Now here's another example of this, and another way that radio waves work brilliantly. If we've got, say, around the world, so imagine this transmitter is in the UK and this receiver is in the north of France. And you were on holiday, you wouldn't be able to receive your short wavelength TV signal or your short wavelength radio signal, because there's no direct line of sight. Okay, there's no way, there's no situation like this where your house or your car or whatever you're in can receive that signal. So we're relying on the longer waves. Now, a lot of times I see a mistake with this, saying that the long waves have got a longer wavelength so they can travel further. It's not because of their longer wavelength that they can travel further. It's because of this effect like diffraction. But also there's a really cool effect, which is that our atmosphere actually reflects some and refracts some of the radio waves. So there is a band of the atmosphere, it's actually slightly charged, and what happens is there is refraction, so bending and reflection of those radio waves, and so they can be received by the receiver. So that's why when you're on holiday in the north of France, you might pick up long wave radio, but you won't pick up a short wave. So that's radio waves. Microwaves are a little different, but not very. So their frequency is 300, now I'm going to write this time with my prefixes, 300 megahertz to 300 gigahertz. So there's a little bit of overlap in terms of the wavelengths, microwaves and radio waves. Wavelength is between 0.001 metre, that's about 0.1 of a centimetre, to 1 metre. And again, they are electromagnetic waves, so they have the same properties. They travel at the speed of light, they can be reflected, refracted and diffracted. Now we use microwaves for two things, cooking and communications. So let's look firstly at my lovely chicken in the oven here. Okay, now what is happening is those wavelengths of the microwaves, remember waves are transferring energy. That energy is transferred to the water molecules in the food. Okay, so the electromagnetic wave, the microwave, is absorbed by the water molecules in the food. They vibrate and move faster. They have an increase in kinetic energy, and I'm going to write EK for kinetic energy. And we know that if we're measuring temperature, temperature is a measure of the average kinetic energy. So if the kinetic energy of the molecules of water is increased, then the average temperature has increased, and therefore the food is getting hot and it will be cooking, those chemical reactions that will be taking place to cook the food. And that is how microwaves work. Now, communications. We have our microwave and we want it to be received by our satellite and then retransmitted to another receiver further around the globe. Okay, but it has to pass through our atmosphere. Now today, as I'm sat at doing this, it's a beautiful sunny day. There's not a cloud in the sky, but our atmosphere has a lot of water in it. So we don't want the same microwave wavelength that we used for cooking to transmit our communications. We need a different wavelength of microwaves, because otherwise what's going to happen is as this microwave signal is transmitted through the atmosphere, all that's going to happen is all that water in the atmosphere is going to absorb that microwave radiation and get hot. Not ideal. So we need a different wavelength to cooking, because we don't want the water in the atmosphere to absorb our signal. So there you have it, radio waves and microwaves, the two longest wavelength sections of the electromagnetic spectrum.